So you'll just list out all the set of instructions or the procedures. Okay, so it depends on person to person, as well as there may be many logic to carry over the task. Okay, so we can follow any algorithm. That logic is called as the algorithm. So why should we analyze the algorithm? So because if you follow some logic, so you can follow different algorithms. Okay, so if we can follow different methods, so based on that, so we have to choose the algorithm best fit algorithm we have to choose, or the optimized algorithm we have to choose from among that. Okay, so how to find out the optimized algorithm? So by estimation of the estimation of the resources of the algorithm. Okay, so there are two important resources. So one is the time and the other one is the space. Time occupied by the program for execution, and the other one is the space occupied by the program. Okay, so both levels are little bit complex things. So sometimes if the time is short, the space may be high. Okay, if the space is short, time may be high. Two things are controversial things. So what we have to do means we have to, from that we have to pick out the optimum one. Okay, so that is nothing but called as the efficiency of the algorithm. That's nothing but we call it as the trade-off between the time and space complexity. Okay, so space complexity mainly deals with the volume of memory. So memory, what we speak here is the data where we store in the primary memory. Okay, so and the time complexity, what we speak here is the number of time. What is the time? Total time required for execution of the program. Okay, so here comes the asymptotic algorithm analysis. So the asymptotic algorithm analysis means analysis of algorithm for such complex problems. So we use three important notation. One is the big O notation, represented by the big O symbol. Okay, and then the next one is big omega notation, and the last one is big theta notation. Okay, so which one is called as the, yesterday we have seen the notations as well, and I have explained you about the upper bound, lower bound, average bound. Which one is the upper bound here?
Big Oma.
Big O. Is it difficult or easy one?
Difficult.
Difficult. Okay, it's difficult to find. And what about big omega? It's lower bound, and big theta is average. Okay, so yeah, so we'll see with the example. Okay, so we'll see with the example. So why for time complexity? So first of all, we'll take time complexity. In yesterday's class and lecture, I have just covered the definitions of time complexity. So again, it is nothing but the total time required for execution of the program. So it may depend on the programming style, so programming logic what we use. Okay, so based we should concentrate on, we should stick on with a less number of time. Okay, so we have to execute the program with a minimum time. So we'll see an example here. So here we take the problem statement as to write an algorithm or pseudocode to find the sum of n numbers. Okay, so here we can solve this using multiple options. So we can take different logic, we can follow different logic. So this is one method. Okay, so this is one pseudocode means it is just nothing but an algorithm. Okay, so we are not following any syntax or any particular programming languages, and we are just writing it. Okay, so this pseudocode explains, so here our thing is that our example is we want to find the sum of n numbers, n nature or sum of n natural numbers. Okay, so for that I am writing one function. So this program you see, so here we are just using a for loop. Okay, so we are writing a function, and sum is the function name. We are passing the number of arguments, so the numbers. So for example, if you want to find the sum of three numbers means what will you do? 1 plus 2 plus 3. Okay, so totally equal to 6. So similarly, so we are just getting the number from the user through this argument, and we are just initializing the s is for sum, and we are using a for loop, and s equal to s plus 1. Okay, So S is equal to S plus I. Sorry, it is S plus I equal to 0. This is small I. Okay, S plus I. And so finally you are printing this S. So in this program, see, so if you are writing this program, so this is here you are using a for loop. So what this for loop does, so first you are initializing the value, and in the beginning your I value is 0. Okay, so your S becomes, second, yeah. So here in the beginning your I is 0. Okay, so for first iteration your I becomes 0 and S is 0 and sum S is equal to 0. This is your first iteration. Okay, and the second iteration I gets incremented. So I becomes 1, so S becomes 1. Okay, and third iteration S is 1, so I becomes 2, 2 plus 1, 3. Okay, so totally this goes on and up to the n, up to n. Okay, so if your n is a 5, you'll get 5 iterations. Okay, and finally you are printing the value of s. So here what is happening is, so your input size is high. Suppose your input is actually 100 times, this for loop execution should takes place. Okay, if it is 1,000 times this for loop executes, right? So it is actually taking too much of time, right? So it actually takes too much of time if you are just writing using this for loop. So here the size of the input increases, time also increases. So for example, if you want if you just calculate the time, I'm just putting some using some microseconds. Okay, so I'm using microsecond. Exactly that won't happen. Exactly a different time may take place inside the computer. Okay, suppose for S is equal to 0, this step you are just using 1 microseconds. Okay, I'm just telling everything in terms of microseconds. This is 1 microseconds. Okay, and the for loop, for example, I'm just giving 5 numbers. I'm giving 5 numbers. So for first step, so 5 iterations will take place. So each step will take 1 microseconds. So totally 5 microseconds. Okay, 5 microseconds. And then to print the value, again it will taking 1 microseconds. So totally how many microseconds are needed for execution of this program? If I'm giving 5 numbers to add, tell me. You're giving
7, ma'am.
student 7. Okay, so fine. So 5 plus 1 plus 6, 6 plus 7. So 1 plus 1, so 7 microseconds. Okay, so totally you need 7 microseconds for execution of this program. Okay, are you getting, students? Are you getting?
Yes, ma'am.
Yes. Others? Others, please respond. Can you respond, students? Okay. Sai Pradeep? Sai Pradeep, are you getting?
Ma'am, yes, ma'am.
Ah, yes, yes, fine. Okay. Good. So suppose if I'm writing the same for the same program, if I'm following other logic, okay. So one more pseudocode I'm writing. Okay. So for sum of n natural numbers, you have the general formula, right? N into n plus 1 by 2. That's why max is also very much needed in case of data structure. Okay. So if you want to learn data structure, we need to know the fundamental concepts of max as well here. Okay, so what is the formula used to calculate the n natural numbers? N into n plus 1 by 2. Okay, so here we have to implement the formula. So no need to use the for loop. You can directly implement the formula n into n plus 1 by 2 and print yes. So this step hardly takes 1 microseconds. Okay, so it is also a simple formula implementation. So just to say this time limit, I'm just telling as a common thing. Okay, generally I'm telling, and print yes. So this takes again 1 microseconds. So totally, how much time required here for this execution?
2 microseconds.
2 microseconds. Okay, so irrespective of the number of the numbers. So for example, here if I want to find out the sum of five numbers, that case also I'll get the same time, 2 microseconds. So but in the previous case, if I want to add five numbers, I'm getting 7 microseconds. If I want to add 50 numbers, I'll get how many microseconds then here? This first pseudocode. If I want to add 50 numbers, sum of 50 natural numbers, how many microseconds will it takes?
52, ma'am.
52. Very good. For 50, it takes 52 microseconds. But see this logic. If I want to add 50 numbers, so how much it will take? How much time it takes?
2 microseconds.
2 microseconds. Okay, so which logic is better? First one or second one?
Second one.
Second one. So second one, so the actually it is taking taking constant time. Okay, so irrespective of the that means size, as well as irrespective of the numbers, so it is taking the common time. So if your n is 50 also, it is taking 2 microseconds. If you just take n here, and if you take time on the y-axis, okay, so if it is 2 also, if the number is 2 also, it is 2 microseconds. If it is 10 also, 2 microseconds. If it is 50 also, 2 microseconds. Respective of the count, the time remains constant. Okay, but in the previous case, actually it increased linearly. Okay, the time increased linearly. If you just take the number on the x-axis, if you just take the number on the x-axis, and if you take the time on the y-axis, okay, so for here you have seen for five numbers, it's taking 7. For 50 numbers, it's taking 52. Okay, so likewise it's going on, so it is increasing. It is linearly it is increasing. Okay, so the time is increasing with the numbers, n numbers. So but here the time remains constant. Okay, so the logic you are clear, right? So the second one is good, right? So the point here is we have to recognize the most efficient algorithm. So we may have different set of algorithms. So our main point here is we have to recognize the most efficient algorithm. So the efficiency can be in terms of, we can analyze in terms of space complexity as well as time complexity. So the example what we have seen now, so there we have analyzed the time complexity. Okay, so we have seen the concept of time complexity. So here, if you just execute the same thing in a compiler using a C++ program, I'll show you now. Wait, I'll open an online compiler. I'll share the compiler. Yeah. Can you see? Can you be able to see the compiler?
Yes, ma'am.
Yeah. So here I'm just pasting the code for logic 1. Okay. See, simple C++ code. So you're all familiar with C++ codes. So I think this is a very simple program, so you can write a thing, right? So I have not written with the classes, just I have written the program inside the main function. Okay. So here you are getting the value of n from the user, right? So you are having the n sum equal to 0 and I. So you are getting the value of n from the user, and then you have one for loop is there. Okay. Is it visible, students? Okay. So this is the program. Okay. So if I execute this program, so it is asking to enter the value of n. Okay, listen carefully. Suppose I am entering some value like 100. Okay, so I'm entering it and I'm getting the sum of n natural numbers 50-50. Okay, suppose if I'm giving some higher values, some 1000, 10,000, 1 lakh. I'm giving 1 lakh. Okay, so just entering. So I'm getting the values. So I'm giving some more higher values than this. 2, 3, 4, 5. Yeah. Suppose if I'm entering this, so there you can see it took some time and you got the value. Okay, so that is 1 second, 1 second delay there, right? So once again I'm entering some higher value than this. There previously I entered 8 zeros. Now I can enter 9 0, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm entering. See, it's taking some time. Can you see how many seconds it took? Some 3 seconds, something it took, right? Are you getting, students? Are you getting? Just say yes or no.
And the answer is wrong, right?
The answer you are just getting this natural numbers. Yes, no, no. One second. So this the answer is correct. 7, 2, 3, 4, 5, 6, 7. Yeah, it's going actually the limit. It's going beyond the limit. So the times it is you're getting the negative value. That's all. You're getting the negative sign. Okay, so it is going the beyond the integer limit. So that also will come later. So what to do and all. Okay, so now just concentrate on the space alone, time alone. Okay, so in the previous thing we have given some 9 zeros. Now I'll give you 10 zeros. 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 zeros. Okay, so now it is taking time. See, 1 second, 2 second, 3 second, 4, 5, 6, 7, 8, 9. So it's taking more time. Okay, So it takes more time, and finally you get some value. So it means why you are getting the negative value means it is going beyond the limit. Okay, right. So we'll stop this. So this is taking more time. Okay, so if we are using the second logic, so we'll use the second logic. Using the if we implement this with the formula n into n plus 1 by 2. Okay. So here just will find out the sum of n numbers using the formula, direct formula, n into n plus 1 by 2. Okay, so you have just here also you are getting the value from the user and you are directly entering. Okay, now we'll just execute this, find the value of n. Suppose we are giving some small numbers, giving, and now we'll give the same number, 1 followed by 9 zeros. Okay, so immediately you are getting, right, there is no time delay. Have you noted? You're getting the same answer only. That's because of the limit bound of integer. Okay, so but here you see you're getting the same are getting you're not getting the time delay, right? Have you noted?
Yes, ma'am.
Yes. So that is the efficiency of the algorithm. Okay. So that is what I told. In the first logic, it actually takes, uh, if you are just if your time, if your number is 50, you want to find the sum of 50 natural numbers, it's taking 52 microseconds or in units. Okay. So here it is taking taking constant time. So if it just enter, will run, enter some 10 digits and check. 1, 2, 3, 4. So immediately you got the answer, right? So it is taking the same time, but there when we entered 1 followed by 10 zeros, so it is actually executing, right? So lot of so much time delay is there in the first logic, but in the second logic immediately you are getting the output. That means a constant time is used. Okay, so something is some we have for every algorithm. So this is how we have to find out the efficiency of the algorithm. So time complexity and space complexity helps a lot in finding the complexity. Okay, so finding the efficiency of the algorithm. So we can use these two as measurement scales. Okay, so we'll come back to the PPT. Okay, so can you see? Yes. So we can use this time and space complexity as the measurement tools. Right? So we can use this as a measurement scale and we can measure it. So when we compare the algorithms based on the so we can compare the algorithms based on space as well as time. Time what we have seen now. Okay, so number of operations required, and a space means how much amount of memory required. Okay, so the total amount of computer memory used by the algorithm. So when it is executed is the space complexity of the algorithm. So what is time complexity? It is the number of operations that an algorithm performs to complete its task. Okay. So sometimes some algorithms require equal time, constant time, as we have seen. The second pseudocode, it is occupying same time, right? And the first pseudocode, it is just occupying more time. Okay, based on the numbers. So if the number is high, it's occupying more time. If the number is less, it is occupying less time. So the algorithm that performs the task in the smallest number of operations is considered as the most efficient one in terms of time complexity. So in our case, whatever example we have seen now, so which one is the efficient one? Algorithm 1 or 2? Which is the efficient one?
Second one.
Second one. So that what we have implemented using the formula n into n plus 1 by 2. Okay. So, however, this space and time complexity are also affected by other factors. So we can't tell that. So this may be only because of the code lines. So this may also be affected by the other factors like computer operating system, hardware. So the processors what we are using. Okay. So 5 gen, 7 gen, 10 gen. So all this depends on the, all this also affects your time and space complexity. Okay. So it is not only the lines. So we'll take one example. We'll compare two different algorithms. So which is used to solve a particular problem. Like we'll take linear search and binary search. So in your C++ last unit, you have studied linear search and binary search, right? So we'll take the two algorithms. So once again, I'm explaining this with this linear search and binary search. Okay. So the first case I explained with the program. Okay. So we used a for loop in the program for the same logic, and we used a formula for the second algorithm. Okay. And we found that the second one is efficient. Okay. So similarly, we'll take linear search and binary search. So to search a number. So if you just take a linear search, okay. So when you go for linear search, what is linear search? Can anyone tell me what is linear search algorithm? What is the linear search? Searching a number, right? So in an array, if you are searching a number, how it will search in a linear search, it will compare each element of the array to the search digit. Or if you want to search something, so it will compare, every element is compared with the search digit. So you would have seen elaborately in your C++. So in our coming topics also, we have this linear search and binary search. So again, I'll explain it. Okay, so now let us count the number of operations it performs. Suppose if you have 10 numbers in an array, and if you want to just to say 1 to 10 you have, okay, and if you want to search the number 10, so 10 is at the last. Okay, so here, so let's count the number of operations it performs. So here the answer is 10, so it compares every element of the array. We want to find out where the 10, where the digit 10 is. Okay, so in the number in the array 1 to 10, it is arranged in an ascending form. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is present at the last. Okay. So linear search uses 10 operations to find the given element here if you want to find out 10. So that is the maximum number of operations in this array. Okay. Suppose if you want to find 1, it can use only one operation. If you want to find 5 here, it needs only 5 operations. Okay. So if I want to find 10, that is the worst case. Okay, so today we have seen the upper bound or big O notation to just to represent the worst case of the algorithm. So and also one more thing you keep in mind. So if you can find the worst case, that's enough. Okay, in an algorithm, it's not at all mandatory to find out the best case and the average case. So if you know the worst case, so you can modify the algorithm and you can make it for far better. Okay, and find you can take out the, you can predict the optimum algorithm, right? So we'll give more importance to this big O notation, okay, because it shall be used to find out the worst case of the algorithm. So linear search take n number of operation in its worst case. Suppose if you see binary search, so binary search for the same thing, so it actually how the binary search does this operation. So it easily, you all know that if you have some 7 or 8 numbers, it divides into 2 and it will search in the search like compares. Okay, so whether the number is less than the middle number or whether the number is greater than the middle number by picking up a middle number. Okay, so that is the logic. So if you try this logic, so when you compare the search digit with the middle element of the array, so what will you get means you can easily get it. So but you'll get the actually the number of operations, it shows a logarithmic relation. Okay, this will detail and when you take linear search and binary search, how you are getting this logarithmic relation. Okay, just keep in mind. So for linear search, it is actually if you are having, if you're, it is equal to the number of elements. Okay, it is a worst case, it is nothing but the number of elements. Here in binary search, it is worst case is nothing but the logarithmic relation of the element. Okay, so time complexity for linear search, we can write using this big O notation as O of n. Okay, and time complexity for binary search, we can write O of log n. This log n story we'll see when we learn this binary search completely. Okay, so with how it varies logarithmically. So far, just keep in mind that so it is varying logarithmically. Okay, but in a linear search, it is equal to the number, the worst case. Okay, this big O notation, it is used to find out the worst case. So it is for linear search, it is order of n, and binary search, it is order of log n. Okay, so here n and log n are number of operations. Similarly, using big O notations, so we have many familiar algorithms. You have also learned at least the definitions in the C++, like binary search, linear search, sorting, quick sort, selection sort, insertion sort, right? Traveling salesperson, right? Lot of algorithms. This, like, except the last one, you have learned all those things, right? So in binary search, it is order of log n. Linear search, it is order of n. Quick sort, order of n into log n. Selection sort, order of n into n. As traveling salesperson, this last you leave it. So all the other four, you see, we will see in detail. We'll see that is linear search, I explained you. Again, we'll see how we are calculating the time complexity. Okay, so we will calculate the time complexity and we will list it in the form of big O notation. Okay, suppose if I told you one example here, right? Two programs. So here, how can you find out the time complexity? How can you represent? So the first case here, the first pseudocode, it is actually equal to the input size. Okay, so it is order of n. So in the second case, it is actually, it is constant. So we can take here order of 1. Okay, so here the big O notation, the worst case complexity is order of 1 in the second logic. Okay, because it is constant. So here the time complexity is order of n. You got it, students, in both the examples, how I am calculating the time complexity? You got it? Or should I repeat?
And can you please repeat?
Yes, yes. So you understood. So I have given two examples. Okay. So one example is just to find the sum of n numbers. Okay. If we are going to write an algorithm, so there we have seen two algorithms, or two logic, or two pseudocodes. The first logic is using for loop, and the second logic is using the formula. Okay. And then again, we have written one more, we have also examined on another example where linear search and binary search. Okay, so linear search, it is searching. Okay, so here when you take this example, when you take the first example, this programming example, for loop, we are getting, and the size of the input is increased, the time is also increasing. Okay, for example, if you are using 5 numbers, you want 7 microseconds. Microseconds, I mean, generally speaking. Okay, it is not the exact time what the computer takes. And if you are having 15 numbers, 50 input, you'll get, it requires 52 microseconds. It's taking 52 microseconds. Okay, so likewise it is increasing. So the first logic, it is equal to order of n. Okay, so that worst case we will denote. Okay, so we can denote worst case, best case, and average case. So but first we are concentrating only on the worst case, that is given by the big O notation. Okay, so first case, whenever the time is increased, whenever the number of element is increased, the time complexity is also increasing. So it is equal to order of n. Okay, and you see in the second case, you are directly implementing the formula. Okay, you are directly implementing the formula here. So it is constant. Whatever if you are using five numbers, you are getting 2 microseconds. If the user is entering 50 numbers also, it is 2 microseconds. So we can represent the constant terms by using order of 1. So the worst complexity is order of 1. So every time we optimize, we should optimize the algorithm until we get the worst case to be a best one. Are you getting? So order of 1 is the least thing. Okay. Even though it is the worst case, you are getting order of 1, but it's best. You getting? Are you getting, students?
Yes, ma'am.
Yes. So now you understood how I calculated the complexity. Okay, data structure is complexity, time complexity, and space complexity. For we have to calculate for F3 algorithms. Okay, right? Okay, all of you got this? Okay. So
Yes,
now,
ma'am.
yes. Now you see, for similarly for linear search and binary search. So if you take linear search, it is equivalent, right? So if the search value, as I told, if you have 10 numbers arranged 1 to 10 in ascending order, if I want to want to search 10, I have to compare 10 times. If I want to search 1, I have to compare 1 time. If I want to compare 5, I have to search 5 times. Okay, so linear search again, it is complex, so it is represented by order of n. If I have 100 elements, if I want to find 100, I have to check 100 times. Okay. But for binary search, how I am searching? I am dividing by 2, taking the middle value and comparing the middle value with the search digit, and then I am omitting if it is less than, if the number is less than the digit, I'll be omitting the higher part and I'm taking only the lower part, and then again I'm dividing the part into 2, and then again I'll continue compare. Okay, so it is logarithmically varying, and you'll get order of log n for binary search. Okay, so when you compare linear search and binary search is better because of this complexity. So similarly, you can find the time complexity of all algorithms using this big O notation. So this big O notation we have seen already. So for this is actually worst case complexity, and for best case we can use this big omega, and theta is for average case. Okay. So constant time, if it is the time is constant, you can represent by order of 1. If it is linear, you can represent that that means if the input is increasing and the output is also increasing, output in terms we take it as time. Okay, so we can take it as order of n. Okay, so if it is logarithmic, we can take order of log n. Quadratic also will get order of n square. Cubic also will get order of n cube. Okay, so big O notation, it measures the worst case time complexity or the longest amount of time an algorithm can possibly take to complete. Okay, so how to, this is a way to mathematically represent it. So you are all coding it, but you are not just you're not worrying much on the time required for completing the task. Okay, just like you are writing logic, right? So you are whatever logic, if you are getting the output, you think that is enough, but that is not the right thing. So you have to get the output with the most efficient algorithm. Okay, so I stop with this. So in the next class, we'll see something about space complexity, and then we'll move to linked list. Okay, student. Hope you got today's lecture. You got the things today. Got it, students? Yes or no?
Yes, ma'am.
Okay. Right. Please interact. Okay. Right now. So I'll take attendance and leave. So it is only 3 minutes. Once again, I'm not from Edisur. Alan,
Present, ma'am.
Anson,
Present, ma'am.
Vishnu,
Present, ma'am.
Vairamuthu,
Present, ma'am.
Karthikeyan, Berwin,
Present, ma'am.
Present, ma'am.
Sharon,
Present, ma'am.
Shakti Srinivas.
Ma'am, he's present. He has a network issue.
Okay. Sai Pradeep,
Present, ma'am.
Amarnath,